Okay, so lecture 8. Now we want to address something which we started talking a bit when we introduced the Lie derivative. So the directional derivative of a vector field. Given a vector field, that symbol is not the right one, we would like to give, so that should be, they should be Gothic XM, but anyway, we would like to give a meaning to its directional derivative at P in the direction given by a tangent vector at P, like we did with functions, no? With functions, we started everything by defining the whole business started by defining the directional derivative of a function on a manifold, on a submanifold over n. So taking a curve that had that tangent vector at the point and differentiated the function along the curve. A reason for this is the classical definition of the Hessian, which I'm not writing in classical terms. In RK, if you denote by del squared f the Hessian matrix, nabla squared of f, the Hessian matrix at x, then V transpose times the Hessian matrix is the directional derivative of the gradient along V. V transpose just because the gradient should be a column vector, but anyway. So if you apply, the Hessian is a symmetric form, it takes two vectors. If you fill one of the inputs with a vector V, the result is a vector which is the directional derivative of the gradient along V. You can prove it easily. So, for example, we would like to have the directional derivative to talk about the Hessian of a function on a manifold. Okay, naive definition. The directional derivative of x in the direction yp is the limit for t that tends to 0 of x gamma t minus x at gamma 0 over t with gamma a curve such that gamma 0 is p and the tangent vector of gamma at 0 is yp. That's the definition we give for functions. Here there should be f of gamma t, f of gamma 0. So the point for a vector field is the subscript, so it's the definition for the function. The difference you have at the numerator makes no sense. We already talked about it. Because in an abstract manifold, x gamma t and x gamma 0 live in different abstract vector spaces. Not only in different subspaces over n, really in two vector spaces which are defined as different objects. So we don't have an operation. They are not inside the bigger ambient where you have a meaning for the subtraction. So this is the main problem. Now, we have the Lie derivative, which kind of does the trick, but it's not really okay. So the Lie derivative, we recall, is obtained by moving x along an integral curve of the flow of y. Okay, full of errors today. Flow of y. So we use the local flow of y to move x along the integral curve of y. So we take x from another point, x of gamma to t, we bring it back to tpm, and we can subtract xp and x gamma of t. We have some problems. First problem, we cannot do it just with the tangent vector. We need a local vector field. So we cannot take the Lie derivative of a vector field with respect to a vector. We need a vector field and another vector field. Whereas for the partial derivative of a function, we just needed the tangent vector at the point, not a vector field. We didn't even know what a vector field was at that time. Second problem, just really a computational one. I mean, if you look at the local expression, you remember the Lie derivative is just the commutator, and the commutator involves the derivatives of both the fields. So you are deriving the coefficients of x and the coefficients of y. So it's a bit weird. It's a bit weird because we would like something that works more or less as a dot product, like the directional derivative in Rn, which is the dot product with the gradient, or the directional derivative of the gradient, which is the dot product with the Hessian, and so on. Third problem, it does not depend only on the values of y along its integral curve through P. So, if you have your local vector field y, you take the integral curve, which is unique because ODEs, etc., going through P, the point P. Now, you have to bring x back along the curve, okay? And that's the definition. However, if you have two vector fields, y and y prime, which coincide, which have the same integral curve and coincide on it, this does not guarantee that the lead derivative of the same field is the same. Example. Take, well, x should be y. Well, anyway, x partial 1 and x prime partial 1 plus y partial 2. So on the x-axis, they both are partial 1. So they're both tangent to the x-axis, the horizontal axis in Orchard. The integral curve through the origin is the horizontal x. Is gamma t equal t0. And x and x prime at t0, so at all the points of the integral curve, are partial 1. However, the lead derivative of partial 2 with respect to the first field is 0. The lead derivative at all the points of the curve, the lead derivative of partial 2 with respect to x prime is minus partial 2. So the lead derivative is not a pointwise operation. It depends on the local behavior of both vector fields, not only on the local behavior of the one you're differentiating, but also on the local behavior of the one you're using as a mean to transport the other. So this doesn't really fit in our desiderata for a derivative. I hope you all agree with that. So it's a weird thing, okay? So we could think about doing an analog of what we do with the differential of a function. So for every smooth function, you have the differential, which is a section of the cotangent bundle, such that for each point and each tangent vector at that point, the directional derivative of f along that vector, just the vector, is the differential applied to the vector. This works because if you have a function from M to R, the differential, which is in so the push forward, is defined from the tangent bundle of M to the tangent bundle of R. And the tangent bundle of R is just, well, R times R, but then if you fix a point, you go from the tangent space of M to, so that's wrong. But if you fix a point, you go from the tangent space to M to the tangent space to R, which is, that is R. Okay, anyway. So the FP is a linear functional on the tangent space. If we take a vector field, it is a function from M to the tangent bundle, so the differential is a linear map from the tangent bundle, well, is a linear map from the from tangent space at P of M to the tangent space at XP, X of P of the tangent bundle. This is the tangent, so you have a smooth map, which is dx, the whole dx, it should be a P here again, So you have a smooth map, which is dx, from the tangent bundle of M to the tangent bundle of the tangent bundle of M. Now, if you think about it, if M has dimension k, its tangent bundle has dimension 2k, so the tangent bundle of the tangent bundle is dimension 4k. It's really growing uncontrollably. And even if you fix the point, the tangent bundle of M then is Rk, the tangent space of M is Rk, the tangent space to the tangent bundle is R2k. So it's weird. So again, you get this thing, and it doesn't work. Why? Why it doesn't work? Because the directional derivative of a vector field, in our mind, should be another vector field. Why? Well, because it's the first order correction. So we are sort of doing the Taylor expansion of x along a curve. So we write the value of x in the point plus an increment. To be able to do plus an increment, the increment has to be in the same vector space, so in the tangent vector space. So it's not working. Now, what happens in Rn? So we take an open set in Rk. Okay? The tangent bundle is U times Rk in a natural way. What does it mean, natural? It means that, okay, no, it's too difficult to explain. It means that two people in the world will do the same splitting. If you ask two different people in the world to write down this product, they will write it down in the same coordinates. Now, given a vector field on U, so now we use the language of manifolds for just an open set in Rk and see what happens. Given a vector field, so xi partial I, the value of the vector field at P is P, comma, x1, xk, because the vector field is a section, so it's a map from M to the tangent, from U to the tangent. So the tangent bundle is the set of pairs, point in U, tangent vector. So the first part is a point in U, the second part is a tangent vector. So the only way to get a smooth map is to consider both these things. Which, again, in Rn, they stay separated really well and naturally separated, but in a manifold they mix up. And that will be the problem. We take the differential. Taking the differential, we obtain this thing. So the differential is just the Jacobian matrix, which is the identity here, and the gradient of this vector map, the Jacobian of this vector map. Okay? You will all agree, I think, that the interesting part is the second one, this one. Okay? So we really don't care about the first identity part. What we're interested in is the second part of the matrix. So obviously here we can just take it out and consider just it, but how could we do it intrinsically, so in a theoretical way, not just selecting the coordinates? Now, we have the projection of the tangent bundle on U. So U times Rk projects on U. And in this case, it's just a stupid projection on the first coordinate. The differential is a map from the tangent of the tangent bundle to the tangent bundle. You can decompose everything again. And the differential of the projection is again the projection on the first factor. Now, we can also, naturally, because it's a product, project on the other factor, Tu. Which is Rk, and which gives you this part here. So the differential of x the directional derivative of x in the direction y is what? Is taking this map, applying it to y, so sending it in the tangent of the tangent bundle, and then taking the projection v. And this will give you back a section of the tangent bundle again, because you're projecting on this factor. In coordinates, you're just writing this formula, which is the sensible one. So the directional derivative is just taking the jth partial derivative of xi and multiplying it by the jth coefficient of the direction. But under a theoretical viewpoint, you are considering this splitting. So you have the manifold and the tangent. Okay, it's vertical with the tangent. You take the tangent to this thing. Inside of this, you have again this factor and another factor u. You can project on the first factor and you obtain the identity. Projecting on the second factor, you obtain an element of the tangent bundle of u. So in Rn is everything is quite unnecessary, because I mean there is a nice vertical line here that tells you, okay, you forget this part and you just take the other part. But in general, it's not that easy. In general, it's not true that the tangent bundle splits, that's the technical term, in a product of the manifold times Rk. This happens only if everything is trivial, like in this case. In general, it does not happen. What do we have in a general manifold? We have only the projection and its differential. So we don't have the two factors, we just have the vertical one. And having it, we can use it as a kernel of a projection, and so we can project on the other one. But we don't have the complement. So, definition, horizontal subspaces. Tm, the tangent bundle of a manifold, is locally u times Rk. So if you take a coordinate chart on M, you have a local frame, etc. And so you have a splitting. You have u times Rk on those coordinates. If you change coordinates, the splitting changes. And the u here won't glue with the u on the other, the v of the other open set. What glues up very well is the other distribution, the vertical one, the kernel of the projection. So given the projection on the tangent bundle to M, we consider the differential of the projection, which goes from the tangent of the tangent to the tangent. And we define the vertical distribution, which is the set of point of the tangent bundle, tangent vectors of the tangent bundle, such that the tangent vector is the kernel of the projection. So it's the collection of the kernels of the projection. This is called vertical distribution. Now, to do what we did in the previous example in Rk, we need something to that projects on the vertical distribution. And so we need a kernel for the projection on the vertical distribution, which we call horizontal distribution, or at least horizontal subspace. So given a point of the tangent bundle, a horizontal subspace is a subspace of the tangent at that point, which is in direct sum with the vertical distribution at that point. So it's a complement of the vertical distribution. A connection, following the definition of Ehresmann.
Potresti tornare un secondo alla slide prima?
Certo.
Mi ero perso l'ultima definizione. Quindi la vertical distribution prendi, ok, dettagli del kernel.
The vertical distribution is the distribution of the kernels of the projection map.
Okay.
So at every point, you have a projection map, you have the differential of the projection map, you have its kernel. The horizontal distribution is a choice of a complement in each tangent space. So if you have a vector space and a subspace, you can choose the complement in many ways, no? There is not a canonical way. Any of these choices is called horizontal distribution. So it's indirect sum, so it means that it intersects the vertical one only in the origin, and the sum is the whole tangent space at that point. So at this point, this is just a subspace. Now, if you glue them up all over the manifold, you get a distribution.
Right.
I mean, it's just a name. But by the way, distribution is another name for bundle.
Okay.
Somehow. They're not exactly the same thing, but here they are the same thing. Just only the name is distribution because it's very old, so people were calling them distributions.
Okay, thanks.
Because the Eresman, he was a student of another guy from differential geometry, like Frobenius maybe, or something like that. So now a connection is the choice for every point of the tangent bundle of a horizontal distribution, horizontal subspace. Obviously, a smooth choice. Everything we do is C infinity. So it depends on the point on the tangent bundle. So it depends on the point on the manifold and on the tangent vector to the manifold. And it has to depend smoothly on both. And this is called horizontal distribution, HTM. Now, a point in the tangent bundle is always of the form point of the manifold, tangent vector to the manifold. An Eresman connection is called linear or affine. Well, here it depends. The name vary a lot. If H as a function of the point on the manifold and the tangent vector to the manifold varies linearly with the tangent vector. So if you fix the point on the manifold and just change the tangent vector, you, in principle, you have different points of the tangent bundle, and you have different horizontal distribution in the tangent of the tangent bundle. These should vary in a linear way with respect to the tangent vector part. If you don't understand this, whatever, I just need it because we will be interested only in linear connections. But anyway, you can write it down in terms of differential of dilations, but it's not technically important. It's a subfamily of connections. Now, why does it work? And there is a connection, so you have your horizontal thing everywhere, so you can project on the vertical. Because whenever you have a direct sum, you can project on either of the direct addends. Summons. Well, factors seem wrong because it's a sum. But anyway, so you have a splitting, you can project on the vertical part and on the horizontal part. On the horizontal part, you already know how to do it because it is more or less the differential of the projection we started with. What's new is that we can project on the vertical part, and we call this projection V. Now, we have a smooth map from the tangent to the tangent bundle to the tangent bundle to the vertical distribution, which is idempotent. So V composed with V is V. Its kernel is the horizontal distribution. And obviously, at every point is a linear map. So it's actually, at every point is just the linear projection with that kernel. Now, covariant derivative of a vector field. We take a vector field and the connection, so we have this V. We define nabla x as V composed dx. So dx goes from the tangent of M to the tangent of M. You compose with V, so you end up in the vertical distribution. Now, the vertical distribution can be made isomorphic to the tangent of M. But anyway, it's not properly written, but it's not really like that. The tangent, the vertical distribution splits, and one factor is isomorphic to the tangent of M. So upon this identification, we have a map that goes from the tangent of M to the tangent of M. So we have, for every point, we have a linear map from the tangent to itself. The directional derivative of x along yp is the tangent vector nabla yp of x, which is this function, which is again a function from the tangent bundle to the tangent bundle, applied to this vector. This C should be a okay. So again, if you project the differential, you end up with, you have to identify some isomorphic spaces, but you end up with the map from the tangent bundle to the tangent bundle, which at every point is just a linear map from the tangent space to the tangent space. So whenever you give it a vector, it gives you another vector. Makes sense? So a covariant derivative is just this, of a vector field is just this. The covariant derivative of a vector field is, for each point, a linear map of the tangent space. So that whenever you specify which direction you want to derive on, you apply this linear map to that direction, to the tangent vector, and it gives you another tangent vector, which is the directional derivative. Now, the covariant derivative is linear in X. This is quite easy. Well, this is because it's a composition of maps that pointwise are linear. And if the connection is linear, that weird hypothesis of before, which we will always assume, so we will only be working with linear or affine connections, then you can write this down. So then, if you have a vector field, you can multiply it by a scalar function. It just means that you are multiplying by the scalar at every point. So what happens if you take nabla fx? Well, if the connection, the Ehresmann connection, is linear, this turns out to be f times nabla x plus this tensor product. Now, why this tensor product? Well, because the T star M tensor Tm is the space of endomorphisms of Tm, so the linear maps of Tm to itself. Now, this is something which is always true. For every vector space, V star tensor V is the space of matrices on n times n in a way. Just remember, this space is not the space of products, it's the space of sums of products. Now, in the same way, okay, let's look at it like that. If you take A and B in Rn, and you do the wrong dot product, so you take A times B transpose. What is this? This is a rank 1 matrix. Now, B transpose is exactly an element of the dual. You remember the transpose means just going to the dual. So this is actually one of the generators of this space. It's a tensor product between A and the functional defined by B transpose. And I think you all know or met this thing in some time, that you can write every square matrix as sum of these matrices, which are rank 1 matrices. Why? Well, because if you just do AI times AJ transpose, you get the matrix which has all zeros and 1 in the point IJJI. Now I don't want to think about it. One of the two. So these matrices contain a basis of the space of square matrices. So their linear combinations give you all the matrices. And this is more or less the same thing. How is an element of these an endomorphism? So if you take V in V and F in V star, the action of this tensor product to any other vector W is just f of W. So you take the element of the dual and you apply it to W. Now you get a number, so times V. So you get a linear operator which has image, which is generated by V, and kernel, which is the kernel of F. And this is a linear map from V to V. Okay, so in this sense, all the linear maps from a space to itself are the dual tensor, the space. So now it makes sense, I hope, that the differential of F tensor the vector field, a section of T star tensor a section of T, gives you an endomorphism of T, of Tm. And now this is a sort of Leibniz rule, which you want to have for something which is a derivative. Now, in local coordinates, given a local frame, we write our vector in the local frame, and we apply the Leibniz rule. So we take out the coefficients, and we apply the connection to one of the vector fields of the local frame, plus we take the differential of the coefficients tensor the local frame. If you write everything down, the first part stays the same. The second part becomes the partial derivatives of the coefficients times these elements, which are a basis. These are the equivalent of the matrices AI times AJ transpose. Okay. So this is the part you expect because this is the Jacobian matrix of X. Okay. So this corresponds in our local frame and coframe to a matrix whose entries are the partial derivatives of the coordinates of X. So it's the Jacobian matrix in our local coordinates. The weird part is this one. But if you look closely, or even not closely, this part does not depend on the derivatives of X. It's a linear function of X. Okay? This depends only on the local frame. So we write down the derivatives of the local frame. The derivatives of the local frame are these numbers, these coefficients gamma, I above, kj below, j is the one fixed, dx k time tensor partial I. This is a sum on k and I. We are writing down the matrix. For every j, we have a matrix. So we have 3 indices. And these weird things are called Christoffel symbols of the covariant derivative. They tell you how much the covariant derivative shifts from the Jacobian matrix, and so in fact how it glues from one coordinate chart to the other, because the Jacobian matrices of the coefficients change if you change the chart, because you change variables, you change everything. So they don't glue up in a coherent thing along the manifold. You have a problem. The part that guarantees you that the partial derivatives can glue up is this part here. So this part accounts for how much changing coordinates changes the partial derivatives. The only problem is that these quantities are not the section of anything. Are not giving you, if you take into account the all 3 indexes, this is not the section of any significant, of any combination of tangent and cotangent bundle. You cannot write it down as we did before with some tensor product. It doesn't work. So they're really, I mean, they were used a lot because if you want to do local computations, you have to use them. But they're not an intrinsic object. People loved them for decades and then started hating them because they're not intrinsic. And they are a pain to work with anyway. Now, another error. Parallel transport. So the answer to the original question we started our lecture with. How to compare tangent vectors at different points, because that was the original question. Now, given a curve, a horizontal lift is a curve into the tangent such that if you project it down from the tangent, you get the original curve. And the tangent vector to the lift, so to gamma h, is inside the horizontal subspace at each point. So this curve, the lift, is a curve that travels through the tangent bundle, which is big. So its tangent vector is a tangent vector to the tangent bundle. So it lives in that space, which is the sum of the horizontal and the vertical distribution. Now, a horizontal lift is a curve that projects down to our curve, whose tangent vector is always in the horizontal distribution. If you put it together some rank nullity and the usual stuff about existence and uniqueness of solutions for the ordinary differential equations, the horizontal lift is an integral curve of some sort and is unique once we fix the starting point. So the starting point is half fixed because it has to project down to the point, so it's a point of the tangent bundle which goes down to a given point on the manifold. So as a point in the tangent bundle is of the form P some vector. So the choice we have is that we can choose the starting tangent vector above as a point in the tangent bundle. And this thing exists at least for small t. Now, consider 2 points and suppose that you have a curve between them that you can lift. So for this curve, there exists the horizontal lift from 0 to 1. Now you choose also a vector at P, and you lift, you take the unique lift that starts at P xp. You follow it. It's always horizontal, so the tangent vector is always in the horizontal distribution. You follow it, and you end up above Q. So you end up at something which is Q xq, let's say. Now, xq is the parallel transport of the original vector xp along gamma to q. So these horizontal lifts give us a way to travel from the tangent space at P to the tangent space at Q. And you can prove it that they give you an isomorphism between the two tangent spaces. And now, okay, I don't think I've written it down. So if you have gamma, you can define tau of gamma PQ, which is the map we just described from TPM to TQM. So this is this parallel transport, this horizontal lift transport. Now, suppose that the derivative of gamma at 0 is P, then you actually have the, is YP, then you actually have that the covariant derivative of x in the direction yp is exactly the limit for t going to 0 of tau gamma p gamma t of xp minus xp over t. So in fact, with these, the right, so it turns out that the right concept is not the flow of y, but is this horizontal lift parallel transport, whatever you want to call it, that compares different tangent spaces. And so our covariant derivative is exactly the derivative along the curve once we transport the vector with these horizontal lifts. Now this is a relation which can be verified quite easily. The last thing, now what happens if you have a metric? If you have a metric, it's a Riemannian manifold, we have the parallel transport. The connection is said compatible with G if all the parallel transport maps are isometries between the tangent spaces. So the tangent spaces are spaces with scalar product. If the parallel transport is an isometry between every pair along every curve, then the connection is said to be compatible with the metric. Just taking some derivatives shows you that a connection is compatible if and only if this relation holds. So deriving along, pay attention. I mean, I'm sure you do, but y and z are, x, y, and z are vector fields. So you take the scalar product between y and z at every point. This gives you a function on the manifold, which is the scalar product at every point of these two vector fields. Now you take the directional derivative in the direction of x of this function. This is as taking the covariant derivative of y along x and then take the scalar product with z plus the scalar product between y and the covariant derivative of z in the direction of x. So in this sense, the connection, the covariant derivative, is compatible with the metric. This concept is a bit more like abstract. This is a very, very precise and computable statement. Now, the last step. The torsion of a connection is this thing. So the covariant derivative of y along x minus the covariant derivative of x along y minus the commutator. The Levi-Civita connection of Mg of a Riemannian manifold is the unique connection such that, I don't know what happened here, but anyway, it's not bad. The relation it's a bit small. The relation we wrote down before holds, so the connection is compatible with the metric and it's torsion free. So its torsion vanishes. So taking the covariant derivative of a vector field with respect to the other and then exchanging them is like taking the commutator for all vector fields. Okay? So it has to be compatible with the metric and without torsion. So if you want, relate it to the Lie derivative, because this is the Lie derivative. There is only one linear connection such that these two hold, and this is called the Levi-Civita connection of Mg. For the Levi-Civita connection, the Christoffel symbols are given by some derivatives of the metric tensor. So the Levi-Civita connection is characterized by the fact that the Christoffel symbols are written down only in terms of the inverse metric and the derivatives of the metric. And the second property, torsion free, implies that the Christoffel symbols have this symmetry that you can exchange the two lower indices. But I mean, it's just so this is it. It's even too much probably. And this is what connections are. The computational part is not so important. We didn't do any computation, but I want to stress the role of, let's say, the geometric picture. So you're taking the differential goes into a very big space, but if you project down on a smaller one, you get the identity. So the interesting part should be the other projection. You don't have a way to do the other projection, so you have to choose a kernel for this projection. Once you choose this kernel, you get what's called the connection, so a way to do covariant derivatives. So you have a lot of ways to pick up a connection. And the connection gives you also a parallel transport and is actually just the directional derivative with respect to that parallel transport. But if you have a metric, you have a notion of compatibility with the metric. Moreover, you have a notion of compatibility with the Lie derivative, so of being torsion-free without torsion. And there is only one connection that satisfies both, which is the Levi-Civita connection, which is the connection. I mean, it's not that everyone everywhere works only with the Levi-Civita connection, but in many applications is the only sensible connection to use. And bear in mind that in many books and places, they won't define the connection with the Ehresmann stuff and whatever. They will just define the covariant derivative. So you will see that a connection is a map from the section of a tangent bundle to the tensor product of this and that, such that some relations hold. Defining the covariant derivative is the same as defining the connection with the horizontal subspace. It's the same thing. So you can go both ways. We did this one because I think that the geometric picture of the horizontal and vertical subspaces is more, somewhat more meaning than a list of algebraic properties. But maybe the easiest one was the other one. I don't know. So that's it for the connection.